Hi and welcome to the lesson of partial differential equations. So in continuation of the previous class that we were discussing system of partial differential equations. So we'll take one more example. Uh, in fact, and advanced problems and comparison with the previous one. So the problem is ut plus ux minus 2v equals 0. So let's use this v here equals 0. That is equation 1. And the second equation we have is vt plus vx plus 2 times u equals 0. That is equation number 2. And given that the initial conditions are x comma 0 sine x and vx comma 0 cos x. All right, so these are the initial conditions for the problem. And now we will apply the Laplace transformations on both of these equations. So the Laplace transform on equation 1 implies that Laplace on ut plus Laplace on ux minus 2 times Laplace on v equals 0. So it's su minus u of x comma 0 minus plus du over dx negative 2 times v equals 0. And if you plug in the initial conditions, we'll get su minus u of x comma 0 is sine x, and then plus du over dx minus 2v equals 0. So name it as equation number 3. Now similarly, applying the Laplace transformation on equation 2, we will get Laplace on vt plus Laplace on vx plus 2 times Laplace on u equals 0. And then we have sv minus v of x comma 0 plus dv over dx plus 2u equals 0. And applying the initial condition, that is vx comma 0 is cos x, so sv minus cos x plus dv over dx plus 2 times u equals 0. So we name it as equation 4, right? Now see equation 3 and equation 4, and we can see that it's a coupled ordinary differential equation, right? So we can solve these coupled equations easily. So let us first simplify equation number 1 and equation 3 and equation 4. So here the equation 3 implies that uh, du over dx equals to v minus su plus sine of x, and then equation number 4 implies that dv over dx equals cos x minus 2u minus sv. If I differentiate equation number 3, so what I get is d squared u over dx squared equals to 2 dv over dx minus s du over dx and plus cosine x. And for this dv over dx, we can plug this value of dv over dx from this equation number 4. So we have d squared v over dx squared equals twice cosine of x minus 2u minus sv minus s times du over dx plus cosine x. And then we have d square v over, sorry, it's not d square v, but it's d square u. So it's d square u over dx squared. And we can just take this negative s, or just keep it on right side for the time being, and it will be 2sv minus s du over dx plus cosine x. Since now in this equation only this term is making trouble for us, right? So we want to eliminate this term. So how we can do is that we can just multiply this equation 3 with s, right, and add with this equation. So what we will get is s du over dx equals 2sv minus s squared du plus s sine of x. Now if we add both of these equations, what we will get is we will get this cancelled out, and then after simplifying we will get a second order non-homogeneous linear equation with constant coefficients, right? So it will be plus 2s du over dx and plus du times s squared plus 4 equals cosine x plus s sine x. Now you see this is a simple linear second order differential equation and with constant coefficients. In fact, it is non-homogeneous, but it's easy to solve, right? So we know that we can solve it by making the characteristic equation, finding the homogeneous solution, and then the particular solution, and then adding both of these, we will get u. So I'm writing directly the solution of this equation, and you can just simplify this and check uh, the solution, right? So what we will get here is e to the power negative sx times a cosine 2x plus b sine 2x plus cosine x over s squared plus 1 plus s sine x over s squared plus 1. So this is the solution for u, but since it's the function of s, x, and s, but what we need is the in terms of the function of x and t, so we need to apply the inverse transform. But before that we need to figure out these two constants. So we have to find these two constants. So for these two constants we need boundary conditions, right? So we can for simplicity in this problem we can just consider some kind of boundary conditions that will make it easier to solve this problem. But we can assume any boundary conditions here, or we can take any boundary, different type of boundary conditions, and we will get different solutions for these constants a and b. So let us consider that u of 0 comma t equals sine t, and u prime of 0 comma t equals negative cosine t, right? So now we will take the Laplace transformation of these boundary conditions. So we will get the Laplace of sine t will be 1 over s squared plus 1, and Laplace of negative cosine t, it will be simply it's not negative cosine t, yes, negative cosine t, so it will be negative s over s squared plus 1. Now let's apply the boundary condition. So it's u of 0 comma s, and this is u prime of 0 comma s. So this is u prime of 0 comma s. Now apply here the first condition. So it will be u 0s equals e to the power 0. It will be a plus cosine 0 is simply it will be 1 over s squared plus 1, and this sine 0 will be 0, and it's equals to 1 over s squared plus 1. So this will cancel out, and it implies that a equals 0. So the constant a is 0, and for the constant b, we need to take the derivative of this. So a is 0, so eliminate this whole function from here because a is 0. So it's e to the power negative sx into b sine 2x. So the derivative will be negative e to the power negative sx into the b sine 2x and plus 2b cosine 2x dot e to the power negative sx. So this is the derivative, and then minus sine x over s squared plus 1, and s cos x plus s cos x over s squared plus 1. Since we have to apply 0 comma s here, so this term will be 0 plus 2b minus 0 plus s over s squared plus 1. So this is equals to, that is u prime. So okay, this is not negative, but it's positive, right? So it will be s over s squared plus 1. So now this will be equals to this will be s over s squared plus 1. Here this boundary condition, this one will be applied, right? S over s squared plus 1. So this cancels out, and again what we get is b equals to 0. So these constants here are 0, which implies that u equals uh, cos x over s squared plus 1, cos x over s squared plus 1, and plus s sine x over s squared plus 1 plus s sine x over s squared plus 1. Now we can take the inverse Laplace. So inverse Laplace will be cosine x over s squared plus 1 plus inverse Laplace of s sine x over s squared plus 1. So the Laplace inverse of this will be cosine x dot sine t plus this will be sine x times cosine t. So this is ux comma t here. All right, now similarly we can work out for v of x comma t, and by doing the same procedure we can simply figure out this v of x comma t, and by looking at the equation, see here what we did for u was we differentiated this equation number 3. So we get this equation here, this one, right? Let's call it, for instance, equation A, and then we plug in this dv over dx from equation number 4, this equation, and then again we want to get rid of this 2sv, so we again added this equation to s times equation number 3, right? And then we get a simple second order linear non-homogeneous equation with constant coefficients. So it's easy to solve and apply the boundary conditions and get the desired result, right? So this is the solution for ux comma t. In the similar manner, if we work for vx comma t by taking appropriate boundary conditions, we will get the result as v of x comma s equals to e to the power negative sx a cosine of 2x plus b sine of 2x plus uh, s cosine x over s squared plus 1 minus sine x over s squared plus 1. And if we consider appropriate boundary conditions, and to get rid of this a equals to 0 and b equals to 0, we can simply do it by solving it, and by inspection we can do it for simplicity. So we can do it by inspection, and then we get v of x comma s equals to s cos x over s squared plus 1 minus sine x over s squared plus 1. And then taking the inverse transformation, we get v of x comma t equals cos x dot cos t minus sine of x dot sine of t. And then we can just simply verify this by plugging in the solutions. So by just taking the derivatives and plugging back into the solution, plugging back into the equation. So the solution is sine t cos x plus cos t sine x for ux comma t, and for vx comma t it's cosine x cosine t minus sine x sine t. Right, so by this in this manner we can do it simply, right? So in the next class we will try to take a practical life example, real life example on system of partial differential equations, particularly the telegrapher's equation, that is also called transmission line equation, right? So thanks for watching the lesson, and goodbye.